Welcome back to part 3 of my video series on Ship Construction Stability Level 4 through Transport Canada. What we're talking about today is more information about displacement and how to use tons per centimeter immersion, as well as theoretical understanding of what a block coefficient is. So a quick review from our previous video talking about tons per centimeter immersion. What this value corresponds to is number of tons of cargo, weight, ballast, etc. that must either be discharged or loaded to increase the mean draft of your vessel by 1 centimeter. Why is this useful to us? It can be used to calculate the change in mean draft required for loading and departure. Going back to our previous example from video 2, we're going to go through a sample question here that may be similar to one you see on an examination. We take our vessel, the direct deadweight diagram will follow, sitting at a mean draft of 6.0 meters. How much cargo must be loaded to reach a departure draft of 7 meters? So going back to our deadweight scale, you can see right now we're sitting at a draft of 6 meters. You go over to the rightmost side inside here, towards your tons per centimeter immersion, you see it's 17.87 tons per centimeter. The question asked us to increase our draft to 7.0 meters, so that means we need to increase our draft by 100 centimeters. So to figure out how much cargo must be loaded to do this, we simply multiply our tons per centimeter immersion by 100 to give us an amount of cargo of 1,787 tons. You'll see questions similar to this throughout your examination. They'll be asking you to either discharge or load a certain amount of weight in certain places and figure out the overall change in the loading of the ship. It gets more complicated in these trivial examples when you start working in the ability to determine the final trim of the vessel while you're loading. Moving on to the next topic for the video. So going back to our box-shaped vessel from the previous video, what you see right here is a vessel of length 100 meters, breadth 10 meters, and draft of 1 meter. So theoretical, looks like a big rectangular prism or box, probably similar to a barge, that kind of object. We naturally know looking at this, moving that through the water will be very difficult. As the more box-like you are, the less fine-lined you are, therefore the much more force required to move you through the water. What the block coefficient says to us is essentially a dimensionless quality that compares your own vessel to this theoretical box of similar dimensions to your vessel. It's an example here showing various types of vessels and their corresponding block coefficients. You'll see high-speed planing craft 0.35 to 0.4, a cruiser 0.4 to 0.45. None of these ships actually really exist that much in the picture. Think about the fact that typical bulk carrier operating in the Great Lakes will be a block coefficient greater than 0.9. So when it comes to a textbook definition, I kind of talked about it. It's the ratio of the volume and displacement of a ship to that of a rectangular block having the same length, breadth, and draft. In this case, you can see the formula written down here, displacement divided by length, breadth, and draft. So we're going to do a quick example problem on this that may be similar to one found in an examination. Take, for example, a ship of displacement 6,400 tons, of length 106 meters, breadth 20 meters, and draft 6 meters. Calculating out our block coefficient, we take the displacement 6,400 divided by the product of the length, breadth, and draft, giving us 0.503. So quite a low block coefficient, corresponds to a somewhat fine-lined vessel.